All right, Chapter 5, Track and Track Stresses. Introduction. Chapter 5, Track and Track Stressors, Truck Stresses. Introduction. The track permanently is the railroad on which the train runs. It consists of two parallel rails fastened with sleepers with a specified distance between them. The sleepers are embedded in a layer of ballast, special thickness spread over them, the route known as the formation. Ballast provides a uniform level surface of the terrain and transforms the load to a larger area of the formation. The rails are joined series by fishplate bolts, and they're fastened to sleepers with various types of fittings. Sleepers are specified with this specified distance are held in position by the ballast. Each component of the track has a specific function to help to perform. The rails act as ground that transmit the wheel load to the sleepers. The sleepers hold the rails in proper position, provide a correct gauge and to help fittings and fastenings when transfer the load to the ballast. The formation takes the total load of the track as well as the formation trains moving on it. Permanent weight of the track that consists of the rails and sleepers, fittings, the fastenings, ballast, and formation shown in Figure 5.1. Our Figure 5.1 shows various components of the track. Natural ground on the bottom formation, a 2 to 1 slope, and then a 1.5 to 1 ballast slope with bearing plate, rail, screw gauge, center of the track, railing, and sleeper. In early days, the temporary track used to lay the carry to each other of the building materials construction railway line. The temporary track used to remove subsequently, the track is called the permanent way in order to distinguish the final track constructed for the movement of the train from the temporary track constructed to carry building material. The specifications adopted by the Indian Railway, the various types of railway tracks, and discussed here, the stress developed in the different components of the railway track due to the wheel moving of the wheel load elaborated. 5.1 Requirements of a good track. The permanent way of the track should provide with the comfortability, safe for the ride, maximum permissible speed with the maximum maintenance cost. To achieve the objective of the sound of the permanent we should have the following characteristics. The gauge should have the correct uniform. The railroad should have the perfect cross leveled and curved. The other outer rail should have a proper super elevation to take into account with the central figure force. The alignment should be straight and free of kinks and curves. In case of the curves of proper transition should be provided between the straight and track curve. The gradient should be uniform to the general as possible. The change of the gradient should be followed by the proper vertical curve to provide smooth the ride. The track should be resilient, elastic in order to absorb shock and the vibration of running trains. The track should have good drainage system to student stability, and the track is not affected with waterlogging. The track should have a good lateral strength that it contain maintain stability despite variation in temperature or other structural factors. There should be a provision of easy replacement renewal of the various track components. The track should have the structure is not only is its initial cost low, but also as maintenance cost minimum. 5.1 Track specification of Indian Railways. Most of the railway lines, Indian Railway line, signal lines generally with a formation of 6.10 meters or 20 feet wide with a broad gauge of 4.8 meters or 16 feet wide meter system. Meter gauge. The following is generally stable in areas where clay soil and other type of sinkage soils are found. Most of the track acceptance shown in Figure 16 is except for the 16% broad gauge meter gauge and 20% of the track narrow gauge, which is in on a curve. The maximum degree of curvature permissible is 10 degree on the broad gauge, 16% of the meter gauge, 40% on the narrow gauge. The ballast used the most often broken stone ballast, but in some areas the more coal ash have been used. About 20 centimeters or 30 centimeters or 8 inches to 12 inches cushion ballast normally provided below the sleeper to transfer the load evenly to impart the necessary resilience to the track. The different materials used to construct woods are 31% for the cast iron, 42%, and steel 27%. Experience has shown that the cast iron sleepers are not suitable to high density route. Restressed concrete sleepers have recently developed by the Indian Railways are proposed to progressively laid on Group A and B routes. Sleepers are laid to various sleeper densities varying M plus 7, M plus 4 are 154 per kilometer, 1300 to 1310 per kilometer. Depending on the weight and the volume of the traffic here is M stands for the rail and meters. Meters time plus 7 means 20 sleepers per rail length of the broad gauge and 19 sleepers per rail length for a meter gauge. Rail standardization for Indian Railways, 60 kilometers, 52 kilometers broad gauge, and 90R, 75R, 60R, and meter gauge, 90R, 75R, etc. R stands for Revised British Specification Rails, normally rolled in 13 meters length of broader gauge and in 12 meter length of meter gauge. The rails welded together longer rail to progressively track in order to reduce the maintenance costs. Noise level they provide more comfortable travel. The rails are welded in depots and three-way panels, normally in flash butt welding method to form a short welded rails or SWRs, or long welded rails are also progressively introduced in various support routes of the Indian Railroad. Railways, their thermite welding is normally done at the side of the convert the short weld into the long weld rail. The fastening used the most screw rail spikes, key, etc. In recent times, elastic fittings such as elastic rail clips and IRN 202 clips have been standardized Indian rails. The turnouts usually normally from 1 to 8 and 5, 1 8 and 1 and 8 and 5 for good trains, 1 and 12 for as well the 61 and 16 for passenger trains. 1 and 20 would be assigned for the sometime back permit higher speed for the turnout side. They have been since discontinued. Curved switches and thick web tongue routes. Thick tongue rails have also been recently introduced in permitting speed at turnouts. 512 recommendation track structure of the broad gauge main meter gauge routes. Indian Railways motorized track structure recent past to meet the challenge of the heavier loads faster track. More than 10,000 kilometers of the track is laid in 60 kilograms rails and more than 4,000 kilometers laid with the concrete sleepers. The present Indian Railway standards of the broad gauge and main meter gauge routes are elaborated with the following section. Alright, track structure. The track Indian Railway broader gauge is classified in 5 broad categories based on speed. They are based on A, B, C, D, E of routes. Also, D spline, E spline routes have subsequently added, explained in section 1A. The track standards of broad gauge have been reviewed, revised from the time based on the obtainable speed traffic conditions. The present broad gauge track structure detailed in Table 1. Various track standard private standard in Table 5.2. Track structures, meter gauge. The track structure meter gauge have been classified and specified in the gross million tons in categories Q, R, R2, R3, and S routes. The S routes of the million meter gauge have further classified in S1, S2, and S3 as per details given below. Routes are through movement of freight traffic is identified as S1 routes. The uneconomical branch is identified in the S3 route. Routes that are neither S1 nor S3 are identified in S2 routes, and the track standards are being not followed. The meter gauge routes are followed in Table 3. Following meter gauge standard specification, heavy haul identified with the movement of 14T axle load wagons should be laid with the minimum standard prescribed by the R1 routes, even if the routes are classified in lower categories. Concrete sleepers, whether provided to have a minimum ballast cushion of 250 millimeters. New rails should be laid at the light welding rail, and control sleepers should be used with a light welded rail as far as possible. Release rail to the higher section up to 90 rails must be used. Prescribed with the section rails not available. Released on broader gauge CST9 Central Standard Track 9 series sleepers NR 90R may be used. Secondary renewals of Q on all other meter gauge. 5.2. Maintenance of the permanent way. The permanent way is the backbone any with the railroad. So if you with the comfort traveling public, the primary testing of the proper maintenance facility. A decade ago, the Indian Railway tracks were most recently maintained better, but the packing and the fixed table time around a year. The recent, however, on the account of the faster track, due to the economical consideration, modern methods of the track methods such as measured shovel packing, mechanized maintenance, indirect track maintenance have been tried. Any vague one on some section Indian railways, particularly on high-speed routes. Mechanical maintenance has been introduced about to 14,500 kilometers of the high-density broad gauge route. The rest of the track is maintained through manual labor. The labor force is directly employed with the task about 190,000. About 3,000 kilometers of track is maintained present measured by shovel packing and to improve with the manual packing. The need-based the directed track maintenance, which initiates maintenance work on which with its actual requirement to being increasingly introduced in order to eliminate unnecessary maintenance work in which makes the labor force more productive. About 20,000 kilometers of the track is covered by the system. A major portion of the track, however, that continues to maintain on the predetermined cyclical program manual method of maintenance better than packaging. Full detailed method of maintenance have been discussed in subsequent chapters. Track utilization. With the introduction of the high-capacity bogie wagon, the replacement of the steam locomotives with the powerful diesel electric locomotives, the track has been subjected to heavier axle loads, higher operating speeds during the period of 1950 to 1951, 1994 to 1995. The average density of the track, in terms of net million tons per kilometers per kilometers per kilometer, has increased to 5.24 to 18.4 million on the broad gauge and 1.9 to 2.65 on the meter gauge. This increased track loading necessitated improvement of the track structure, maintenance practices, special overhaul, high density, high speed rates. 5.3 Track and elastic structure. In the year 1888, Zimmerman propounded the track theory of the track as elastic structure. Rail of the continuous beams carried on sleepers was provided with elastic support with elastic nature. Rail support affect distribution wheel load over the number of sleepers in a rather complicated manner. The mode of the distribution load depends on the stiffness of the rail as well as the elasticity of the bed, sleepers, and ballast formation taken together on which the rails rest. 531 Track modulus. The track modulus, like modulus elasticity, is an index measurement of the resistance deformation that defines the load of the kilograms per unit rail length required to produce one unit depression of the rail bottom. The unit of the track modulus kilogram to centimeter squared. Research Design Standard Organization of the Indian Railways has carried out a large number of investigations to determine the track modulus vertical bending stress in the rail due to the strategic loads on the broad and meter gauge. The empirical studies reviewed the rail depression immediately below the low and not directly proportional to the load of the entire load range due to the slack of the voids of the track structure. Track depression disproportionality higher in the initial stage of loading. The slack voids would get closed under the initial load. Therefore, further depression per unit load smaller becomes proportionate and to increase the load. If it was found initial the 4-ton, the broad gauge 3-ton for the meter gauge given the best results. There are those that too well designed load range of the various the track module is not able to completely define the load depression characteristic. The complete relationship being established by assuming the linear load depression relationship as if the initial stage of the load and that the two values of the track modulus, one of the initial track modulus U1 UI and the other elastic track modulus UE. The track modulus varies in gauge as well as the track standards, namely with the type of the rail, sleeper, and density, ballast, cushion. The values in track modulus adapted to the Indian Railway are given in Table 5.4. Alright, your 90 rail and 5.4 Forcing action on the track. A rail is subject to the heavy stress due to the following type of the force: vertical loads, consistently dead loads, dynamic augmented loads, including the effective speed, hammer blow effect, and air reciprocating mass, etc. Lateral forces due to the movement of live loads, essential vertical loading, shunting of the locomotives. Longitudinal force due to the traffic effort and braking F forces, thermal forces, etc. D. The contract stress due to the wheel and rail contact, and NGE stress due to the surface defects as well as the flat spots on wheels, etc. 5.4 Vertical loads. Dead load of the vehicles at wheel contact. The value of the dead load is usually taken with the axle load of the diagram. However, with the various reasons, actual wheel loads, even when the statistics say of the level of the perfect track, may be different from the normal van wheels code. This happens sometimes when come into the notice that the steam locomotive has a higher axle load for nominal load have different right and left wheel loads. The dynamic augment of vertical loads. Once of the vertical impact due to the speed of the rail vibration, the dynamic load is made more of the static load. The dynamic wheel load is obtained by the increasing the static wheel load by an incremental amount given by the speed factor. Until 1965, the Indian Railroads used the Indian formula calculating speed factor. The formula follows as speed factor equals V over cubed root of initial track modulus. V is speed in miles per hour. UI the track modulus and PSI. At 1969, the German formula of the G given by Schramm was adopted, which was as follows: for speeds up to 100 kilometers per hour, speed factor equals the velocity squared over 30,000. For speeds over 100 kilometers, speed factor of 4.5, the velocity squared over 10 to the fifth minus 1.5 velocity cubed over 10 to the seventh. Where the V is the speed of the kilometers per hour. As in speed of 60 miles an hour, Indian formula give the speed factors up to 55%, where the German formula, as used by the Railroad Research Design Standard Organization, gives you 30%. Investigation Research Design System Organization, different value of the speed factor have been recommendation, different type of the vehicles running different speeds. Or your hammer blow effect. The central figure force is due to the revolving mass of the driving the coupled wheel with the locomotive such that the crank pins, coupling rods, parts of the connecting rod are completely balanced by placing the counterweights near the rim of the wheel, dynamically opposite of the revolving masses, reciprocating mass of the piston rod, crosshead, and part of the connecting rod. Virtue with their inherent oscillatory movement, provided with alternative force in the direction of the stroke, tend to cause the locomotive to oscillate sideways, not nose across the track, in order to reduce the nosing tendency. A weight is introduced onto the wheel of the opposite side of the crank on this horizontal component, with the central figure force of that of the weight balance and inherent forces in the line of stroke, but the vertical component throws the wheel out of balance and plane perpendicular with the line of stroke. The vertical component of the central figure force of the wave, with the introduced balance of the reciprocating mass for the causing variation of the wheel pressure on the rail with the call of a hammer blow. The heavier the weight of the added to the balance of the reciprocating mass, the greater the hammer blow. The hammer blow effects occurs only in the case of the steam locomotives, and the hammer blow can be calculated as is figure 5.2. Hammer blow equals M over G R 2 pi n squared sin 0, where M is not over with in pounds, R is the crank pin diameter in feet, and N is the number of revolutions wheel per second, and 0 is the crank angle. 5.2 shows the steam effect hammer blows effect in an air reciprocating mass, the hammer steam effect hammer blow, and effect of the air reciprocating parts. Your steam effect. Locomotive working with the converting with the coal energy and the steam energy. The steam protect the pressure acts of the piston transmitted to the driving wheel through crank pins and connection rod. The vertical component of the crank pins connection rod angle of the piston rod value of the given formula. The vertical component equals pi over 4 d squared p equal over p times r sin 0 plus negative h plus or minus negative h over L, where L is the length of the connection rod and inches, H is the crosshead above the center line with the driving with the wheels, and inches 0 of the crank angle, the angle transverse of the crank since the beginning of the stroke. The steam effect does not synchronize with the hammer blow effect over the balance additional hammer blow only during some of the parts of revolution of the crankshaft. The inherent reciprocating mass. The reciprocating mass due to the inherent acceleration alter the force for the piston, hence the force for the connection rod as effective during the revolution of the wheel. You have FV equals M over GR 2 times pi in squared bracketed cosine 0 plus R over L cosine 2 0 times R sin 0 plus or minus H over L, where M is the reciprocating part of the L of the length of the connection rod, N is the number of the revolutions per second, H is the length of the crosshead above the center line with the driving wheel, and O is the crank angle, the maximum combined fat force of the hammer blow, steam effect of the narrow each of the driving wheel, hammer blow effect of the couple wheels does not actually simulate due to the phase of the difference of the angular position with the counterweights is into the couple of the driving wheel. The maximum combined effort of these forces obtained, summing up the three curves of the one of the complete revolution over the wheel. Bending of the stress of the rail due to the vertical load. The general theory of the bending is made from the assumption of the rail with the longer bar continuously supported with elastic foundation due to the vertical loads and rail subject to the bending of the flexural stress of the bending stress of the rail with the subject of the result of the vertical loads and illustrated in figure 5.3. The theory of the stress in the rail takes into account the elastic nature of the support based on their theory of the formulation of the bending of the moment is n m. The bending moment equals 0.25 times p, which is isolated vertical load E times to the negative x over L square power times bracketed sin x over L minus cosine x over L is the characteristic EI of the flexural stiffness of the rail. U is the track modulus. X is the distance for the point from the load. According to the equation, the bending of the amount of the zero is where the x equals pi at 1 L over 4 times 0.3 or 3 pi over L4 maximum with a x over 0 XL2 and 3 pi XL of 2, etc. This is the FMB percentage of the maximum bending stress of vertical loads. The calculation stress acting on the rail with the first maximum bending moment caused due to the stress here of the load moving the rail is calculated per equation 5.7. The bending of the stress is calculated dividing the bending of the moment and with the second sectional modulus of the rail. The permissible value of the bending stress due to the vertical load eccentricity of 23.5 kilograms of millimeter squared for the rail is 72 UTSs. 542. Stress is on the track. The track is due to the various kind of the force applied with discussed in the following sections. Lateral force. Lateral force applied with the rail head produces lateral deflection twisting the rail. The lateral force consists of the rail to bend horizontally, resulting in torque caused by the huge twist of the rail as well as the bending of the head and with the rail with lateral deflection of the rails. Resist the friction between the rail and the sleeper. The resistance offered by the rubber pad and fastening as well as the ballast coming in contact with the rail. The combined effect of the lateral forces resulting in the bending and twisting of the rail can be measured in straight gauge. The field trail to indicate the load rail wheels of the locomotive may exert lateral force up to 2 times the straight track, particularly at high speeds. Longitudinal forces. Due to the tractive effort of the locomotive, the braking force, longitudinal stress that develop in the rail, the temperature variation, particularly in wealth, will result in the thermal forces, which also lead to development of stress. The essential magnitude of longitudinal forces depend on many of the variable factors. However, the rough idea of these values are followed. Longitudinal forces account for the 30 to 40% of the weight of the locomotive, the traffic effort, and alternating current. Longitudinal forces account for 15 to 20% of the weight of the braking force, the locomotive, 10 to 15% weight of the trailing load. Tensile strength will include the winter due to contraction, compression, and the stress that develop in summer due to the compression. The stress view of the stress can be used in 10.75 kilograms meter squared and weight of the 9.5 kilograms meters in summer. Your contact stress between the rail and the wheel. Hertz formulated with the theory that determines the area of the contact of the pressure distribution surface of the contract between the rail and the wheel. As per the theory of the rail, the contact is similar with the two cylinders. A circular wheel end curve ahead with the rail with the axis of the right angles to each other. The area of the contact between the two surfaces is bound by an ellipse shown in figure 5.4. The maximum contact of the shear stress F is the contact point between the wheel of the rail given in the empirical form. F is equal to 4.13 over PR to the power of 1.5. Whereas F is the maximum shear strength of the kilograms meter squared. R is the radius of the fully worn out wheel in the millimeter. P is the static wheel of the load in kilograms times 100,000 kilograms for unloading of the curve. The contact stress of the WM2 locomotive static wheel P is equal to 940 plus 1,000 equaling 10,400 kilograms. Radius worn out wheel with a maximum of 76 millimeters or 38 millimeter radius reduction. Alright, figure 5.4 shows the contracting stress relay, shows the formula we just talked about with the wheel assumed to be as the center of the top surface of the rail, the part of the cylinder X, Y, and Z, and R. The contact stress WMD2 locomotive is such as the 18.7 kilograms millimeter squared. This maximum value, however, limited to 21.6 kilograms squared. Kilograms millimeter squared, with 30% of the UTS value of 72 kilograms and by equal to millimeters squared over the rail. Alright, surface defects. A flat wheel on the low spot of the rail causes the extresses the rail section. The empirical study of the reveal the additional flexion of about 1.5 times the depth of the flat low spot occurred with a critical speed of 30 kilometers an hour. Additional bending is caused by the account with the value of the 370,000 kilograms centimeters from the broad gauge group of the route within the WDM4 locomotive. The stress on the sleepers are subjected to a large number of the forces as such as the dead and live loads, component of the track, the stretch of the rail, and sleeper fasteners, maintenance standards on such other allied forces. Based on elastic theory, the maximum load on rail seat is given by the following formula. Maximum load on rail seat is equal to P over Z of the track modulus P divided by Z over the track modulus L S equals PS over Alright, when P is the wheel load and U is the track modulus, S is the sleeper spacing, L is the characteristic length, and Z is the modulus of the rail section. Maximum load of the rail seat is 30 to 50% of the dynamic wheel load, depending on the various structure factors, particularly with the packing of the under the sleeper. The distribution of the load under the sleeper is not easily determined. The pattern of the distribution depends on the sleeper as well as the firmness of the packing under the sleeper. The bill and ballast shields under the load. The pressure under the sleeper is not uniform, varies depending on the standard maintenance. The following true extreme conditions may arise. Endbound sleeper. The newly complicated ballast was compacted under the sleeper end of the sleeper. The hard packed. The flexion of the sleeper, the center is moved, then the move is more than the ends. Center bound sleepers. The train has passed over the track of the packing under the sleeper. This becomes loose, becomes a hammering action of the moving of the load. The sleeper then turns to loose under the rail seat. Ultimately, due to the defective packing, sleeper is sometimes hard packed in center. Alright, stress is on ballast. Load ballast on the sleeper from the rail. The return transformed to the ballast. Efficiently, the load transmission depends upon not only the elasticity of the sleeper, but also the size, shape, and the depth of the ballast, as well as the degree of the compaction under the sleeper. Professor A.N. Talbot had analyzed the pressure distribution ballast under the sleeper, and the investigation revealed that the pressure of the distribution curve under the sleeper would shape as like bulbs as shown in Figure 5.5. The following important conclusion is drawn in Figure 5.5. The pressure of the sleeper maximum center of the width and the pressure of the degree for the center toward the ends. Vertical pressure of the sleeper uniform. The depth approximately equal to the space of the sleeper. The pressure in formation of the subgrade. This is the live as well as the dead loads that exerted by the train. The substructure and finally carried by the subgrade. The pressure of the subgrade depends not only on the total quantum of the load, but also the manner in which the transfer to the subgrade. The space between the sleeper and the side, the depth as well as the compaction ballast under the sleeper. Type of the subgrade to play with an important role of the distribution pressure on the subgrade. The maximum formation pressure and permitted with the engine rails are followed. For motive power, 3.5 kilograms centimeters squared. Broad gauge 2.5 kilometers squared. 2.5 kilograms centimeters squared. Meter gauge for good wagons. 3.0 kilograms centimeters squared. Broad gauge 2.3 kilograms centimeters squared. Meter gauge. Our Figure 5 shows the stress in the middle with the depth over centimeters, the distance from the center line of the middle of the sleepers. You have your middle of the sleepers and your sleeper, your ties. Alright, relief on stress. Train load consists of the number of the wheels that close each of them acting simultaneously. A single isolated wheel load creates much more of the bending moment if the rail is compacted with the wheel loads than the account with the negative bending amount with the adjacent wheels provided with the known relief of the stress. The real stress for the case of the comparative, the smaller the value of the relief. This depends on the distance of the point of the contraflex of the rail, placing space between the wheels and between the value of is 50%. Permissible stress on the rail section. The permissible bending stress due to the vertical load and eccentricity and lateral load in the rail section of Indian rails given in Table 5.5. Permissible bending. Permissible stress due to the bending, 3.36 kilograms meters squared and 23 inches squared. Minimum ultimate tensile strength, 72 kilograms meters squared or 46 tensile inches squared. The stress on the rails are measured with the following method depending on the facilities available. Photoelastic method, electro-resistance strain gauge method. The method employed by the using special testing frame. Present Indian Railroad, most usually electrical resistance strain gauge with the measuring of the rail stress. Whenever the new locomotive roll stock design is introduced in the railways, a detailed study is carried out, followed by the field trials to ensure the permitted speed of the new locomotive rolling stock does not cause excessive stress on the track. The same such simulations are made whenever the increase of the speed of the axle loads existing locomotive roll stock design. The various parameters there limiting the values required to be checked in broad gauge are given in Table 5.6. You have your parameter, bending of the stress of the rail, the contact stress between the rail and the wheel, the dynamic overload rail joints to unsuspended masses and formulation pressure, fish plate stresses and bolt hole stresses. 5.5, coning of the wheels. The tread of the wheels of railways is not made fast, but sloped in the cone in order to enable the vehicle to move smoothly on the curves as well. The track, the wheels generally centrally aligned with the straight and level forces, uniform gauge circumference of the tread into the inner and outer wheels are equal. It can be seen in Figure 5.6. The cone wheel shows a slope of 1 to 20 with the rail wheel and wheel flanges 1 to 20 in the rail, slope 1 to 20, 1 to 20, cone of the wheels, inner wheel axle, outer wheel, inner wheel 1 to 20. This problem, however, arises with the cause of the case of the curve without the wheel that is negotiated more distance from the curve of the conveyor for the inner wheel due to the action of centrifugal force of the curve of the vehicle tends to move out to avoid the circumference of the tread of the outer wheel is made with greater than the inner wheel. This helps the outer wheel to travel the longer distance than the inner wheel. The wheel of the vertical wheel railway vehicle connected with the axle will turn with the fixed of the rigid frame due to the rigid frame of the rear axle a tendency to move inward, which does not permit the leading axle to move at the advantage of the coning. The rigidity of the frame however, that helps bring the vehicle back to center alignment works for the balancing factor. The coning of the wheels helps to keep the vertical vehicle centrally aligned with the straight with the level of the track. Is also since slightly irregular track do occur with those resulting in moving the loads vagaries of the weather. The wheels therefore move from side to side and therefore the vehicle's sway. Due to the coning of the wheels, the side movement is the result of the tread of the circumference of one wheel increasing over the other. As both of the wheels transverse at the same distance, this causes one wheel to slide. Due to the resistance caused top of the sliding any further side of the movement to prevent it. If there is no coning, the slide movement would have continued, and flange of the wheel would also have been come in contact with the side of the rail, causing the jerks, making the ride uncomfortable. Coning of the wheels causes wear and tear to even the flipping of the action. However useful, it helps the vertical to negotiate curves smoothly, provides smooth ride, and reduces wear and tear to the wheel flanges. As for slips and concerned, and mathematically calculated slip is equal to 2 pi over the angle over the 360 times g, where z is the angle with the center of the curve the fixed with the rigid wheel box. G is the gauge in meters. Approximate value of the slip of the broad gauge is 0.029 meter per degree of curve. Alright, 5-6, tilting of the rails. Rails tilted inward at an angle of 1 in 20 reduces the wear of the tear of the rails as well as the tread of the wheels. The pressure of the wheel and it acts near the inner edge of the wheel. The heavy wear of the tear of the wheel. Rail lateral bending of the stress also created by the eccentric load of the rails on even load of the sleepers are also keeping the cup. The damage to reduce the wear and tear of the well is the lateral stress rail. The tilt of the 1 in 20, which also slope of the wheel cone. This rail is the tilted to anodizing the wheel wooden sleeper to provide with the canted bearing plates. Alright, summary. The permanent wave that consists of the rail, sleeper, the ballast, and slipper feeding of the upgrade with the strength of each of the components is essential for the safe running of the components. The stress developed with each component due to the movement of the wheel. Load should be permissible load and specify the different type of the track. This concept of load distributing the rail track based on the elastic theory of the most equation that causes the stress for the different components. The theoretical background, the coning of the wheels helps reduce the wear tear of the wheel flange, provide a smoother ride till the ill effects of the coning of the horizontal curve to reduce laying the rails at a slope of 1 in 20. Chapter 6, Rails.